Hello community, great that you are back. We have a brand new paper by DeepSeek published today. Let's have a look. Yes, they explain us here how they built the next generation of DeepSeek models. Published 14th of May 2025. You know DeepSeek, we have the model R1, the reasoning 1 model, and we are all waiting here for the release of the new R2 model. But on the way to the new R2 model, we had at the end of March 2025 the new V3 model, the release here of March 2025 that is now with significant improvements, and this points here the way forward, the vector to the new reasoning 2 model. Maybe it is the base model to the new R2 model. However, today we talk about exactly about this new release. We have a look exactly how it is built. And you know, a lot of people said, no, it is impossible that DeepSeek managed this, could do this, because, all the other companies from Google, XAI, Meta, Microsoft, OpenAI, they need hundreds of thousand GPUs or TPUs, or maybe even more. So it is impossible that such a small startup could do this. And I think DeepSeek beautifully demonstrate now with this new paper that it is possible if you have an effective software-hardware co-design that can enable cost-efficient training of large models, leveling now the playing field even for smaller teams. You don't have to be huge, you just have to be smarter. Now, if you look at this, it is rather simple because you find some elements that we already know, no? We have the classical transformer architecture. We have a norm and then we have the attention block. Then we have another norm and then the feed-forward network. And you say, yeah, that's absolutely what we know. But just if you look a little bit closer at the attention block, you will see it is not our classical self-attention, multi-head center of attention, because here we have a multi-head latent attention. And let's have a look at this in further details. Plus, we have dense model, but also, and this is the interesting part, we have DeepSeek mixture of expert model. And they further develop this. And they explain here how to train it and what are the specialities of this base model for the next R2, the reasoning 2 model. And they developed some technology. They are not just going for the main model for the next token prediction with a cross entropy loss, but they have something special that they apply. And look, you can see that some of the output heads are sharing here results. Plus, we have an interdependence here between the different sequence of input token. Here we have our input token. Here we have the interval from T1 to T4. Then we move here from T2 to T5, T3 to T6. And there is something happening that is beautiful, that enables here a much faster training. So there's a lot we have to talk about. New paper by DeepSeek published today. I told you what is really important, the mixture of expert development and here the multi-head latent attention architecture. And they have in part already been implemented here in DeepSeek version 2, the base model for the R1 model. And today we have a look here at the further development here at compressing here the key value cache structure. Now you remember by DeepSeek version 2, this is here where they explained here, this is version 5 from June 2024. They explained already here the multi-head latent attention, and we already had a look at this particular. And they showed us here, look, it is so much better because if we just have a multi-head attention or a group query attention or a multi-query attention, this new methodology of a multi-head latent attention, where we compress this in a reduced vector space, we can have some real faster computation. Yes, I showed you already here the multi-head attention computation is rather simple, but the implementation is where we really have to be careful. Now, you also know here, talking about the other part here, the mixture of expert, this is here from January 2024, also here from DeepSeek. And they already explained this to us. Now, they have a conventional top 2 routing plus a fine-grained expert segmentation. And then they have a shared expert isolation you see here. And we already had a look at this particular methodology with a shared expert and rooted expert and the optimization we are able to achieve with this particular structure. Now, let's have a look at the current LLM inference. We go now for a multi-turn conversation. So to handle this efficiently, The context from the previous request is simply cached, no? What is commonly referred now as key-value cache. Key-value cache addresses now this challenge by caching now those vectors of previously processed tokens, eliminating the need to recompute them for every subsequent token. And you say, yeah, this is familiar, no? Because the model only computes the key-value vectors from the current token and performs then the simple attention computation by combining them with the cached key-value pairs from the historical development. Incremental computation reduces, and this is the beauty, the complexity of generating each token now to an order of n, making it efficient when processing long sequences like we have in multi-turn inputs or some real complex reasoning. As I told you, with our MLA, we compress now the key-value representation of all attention head into a smaller latent vector space. And we do this here by using here in an intelligent way a projection matrix, which is then jointly trained with the LLM. So during the inference now, we only use here the latent vector. They only need to be cached, reducing here the memory consumption compared to storing here the key-value cache for all the attention heads. And you know there is, in addition to MLA, we have other shared key-value possibilities, like the grouped query attention or the multi-query attention. But as it turns out, if you look here at this performance benchmark, DeepSeek version 3 with a MLA, look at this, the key value cache size comparison per token. Look at this. Version 3 only needs 70K. The Llama 3.145 needs 516K, and the QN 2.572B, so the older one, 327. So this is really an outstanding result here for key value cache. You remember we talked about this paper, the NSA, the native sparse attention. So we have now an optimization for specific hardware, a co-design. And we talked about here that we have here quite a different parallel here, compressed attention, selection attention, and a sliding attention mechanism. And we had a look here at the score computation, was rather easy. But you remember what was nice that we had in this framework here, the input sequence through 3 parallel attention branches. So for a given query, preceding keys and values are processed into the compressed attention for the coarse-grained patterns, the selected attention for the important token blocks, and the sliding attention for the real localized context here. And it worked out great. And then when we looked here at the particular visualization of different attention patterns produced here by all 1, 2, 3 branches, we saw here, as you see here in green, the attention score. Attention scores need just to be computed here in the green area, while the white areas represent region that we can skip in our computation because they do not contain here valuable information that we need to take care of. Talking about costs, this is a new study here that shows us here, look, if you compare here the DeepSeek version 2 mixture of expert with the version 3 mixture of expert, you remember the size here increased significantly from 236 billion to 671 billion. But look at the training costs. Even the model size exploded. We are still in the same region here with the training costs per token. And just as a comparison, look at the dense model, a QN72B. I mean, this is about less than a tenth here, and we have comparable training cost. Or look at a Llama, 405 billion free trainable parameter, also a dense model. This is just extreme, the training cost here per token for a Llama model. So what DeepSeek version 3 mixture of expert achieved here, some extreme reduction here in the training cost for training a mixture of expert models, even compared to dense model. So if quite a lot of people ask, how were they able to do this with those deep understanding and with those optimization? Talking about optimization, what I learned reading the new paper today, and as you see, they tell us here, this is quotation mark, the increasingly popular K-transformer inference engine allows it a complete DeepSeek V3 model to run on a low-cost server equipped with a consumer GPU. So I said, what? I was not aware of this. So we have here a new inference engine. Beautiful. So here we go. We have a GitHub here, a flexible Python-centric framework designed with extensibility at its core. So a RESTful API is compliant with OpenAI and Ollama, even with a simplified ChatGPT like Web UI. Absolutely fascinating. If you look a little bit closer here, you see the performance. For a Llama CPP, you have about a generation of 4.5 tokens per second, and with K transformers, you have 14 tokens per second. So I definitely have to have a look at this because I'm not familiar with this. But if they recommend, especially as you see here, where it was here, May 14. So today they say, hey, we support Intel GPUs, Intel ARC GPUs with a specific tutorial. This is now getting interesting, and they take care here about a consumer GPU. Absolutely fascinating. Yeah, if you want to see this, this is here the K-Transformer GitHub, and we have an Apache 2 license, so it's open source. I am kind of amazed. But then you remember yeah, the very first page where I told you, hey, there's something happening. Look at this. We have now a new multi-token prediction framework to enhance simply the model performance and improve here the inference speed. If we can do this on multi-token and not on just here the autoregressive next token prediction. So here we have our main model, and then as you see, MTP model 1, 2, and 3. So what is this? You remember this publication. This is here from April 2024. And we had here better and faster large LLMs with multi-token prediction. And they showed us here quite a simple methodology. Just look at the formula. No? In a standard language modeling, we have an LLM, beautiful. And the learning objective here in the optimization for this LLM is to minimize the cross-entropy loss that you know. This is a familiar formula. And now, if they do this to predict the n future tokens at once, it becomes a very similar cross-entropy loss you just see here. We just broaden here the interval that we want to predict. And it was a rather straightforward implementation. No? Even here to give us the code here, if you have two heads here, order for the forward backward in an n token prediction model with n equal 2 heads. So this was rather interesting. And now they tell us, hey, we implemented this here for the base model of R2. So each MTP model uses here a single layer, which is much more lightweight than the full model, to predict additional tokens, enabling now a parallel verification of multiple candidate tokens. A parallel verification? This is interesting. Yeah, they say, okay, slightly hurting here the throughput, but this approach significantly improves the end-to-end generation latency. And they tell us here, after they have a lot of testing and a lot of additional information in the paper, please go and read the paper here by DeepSeek. It is great. It's one of the best paper. It's the paper of the month, I would say. They tell us here we achieve here an acceptance rate of 90% for predicting the second subsequent token correctly. 90% is excellent. But they also have another, if you want, deep insight, real clever way, low precision driven design. And you know, we do have quantization techniques, no? GPTQ, AWQ, you can use your 8-bit, maybe you go down to 4-bit if you're really brave and say, I don't care about accuracy. So it all depends on your memory requirement. But you know that these techniques are applied here during the inference to save the memory. No, you have to have the model. And now DeepSeek said, hey, wait a minute. We don't have 100,000 GPUs. If we only have 2,000 GPUs, we have to optimize this. So they went and they discovered a quantization technique not for inference, but for the training itself. And this is now extreme delicate. This is an equilibrium. You really have to understand what you're doing. No? And they just have a simple sentence, no? And through the deep collaboration between our infrastructure and our algorithmics team, and after extensive experimentation, and to give you quite a lot of data in the paper, we develop an FP8 compatible training framework for mixture of expert models. which is great, which is amazing. And you know what? They give it's open source here. Look, DeepGem, library designed for clean and efficient FP8 general matrix multiplication with fine-grained scale as proposed by DeepSeek for version 3. And as you see today, 2025-05-14, DeepGem now offers weight gradient kernels for dense and mixture of expert backward. So there is something happening at DeepSeek. They are preparing something, and I hope, yes, you guess what, we will have a new reasoning model real soon. But therefore, when they published this paper today, I decided I want to show you the paper here right now, because if we have then the new R2 model, it will have its own complication to explain, to understand, to optimize, to fine-tune, have reinforcement learning. Therefore, if we understand the base model for R2, we have a perfect start. If you're interested more or less here, please be aware you have to be really expert here in CUDA. They're talking about a tensor memory accelerator that they developed, how to optimize so you see a dense interplay, a co-design hardware and software design. I put this here in quotation mark because I do not really understand here when they talk here that they have a tensor core which only maintains their highest 18 fraction bit for a particular mathematical operation, and then the large dequantization overhead in transporting here partial results from the tensor core to the CUDA cores for the scaling factor multiplication. I think I have no idea what they are talking here in this particular software package, but hey, why not go there, have a look yourself. It is open source, so you can learn it immediately. GitHub is available for you for a deep dive. Now, I'm interested more in the general new ideas of this model, and let's talk about the communication compression. Authors tell us here, in current V3, we employ here a low precision compression for the network communication, because remember parallelism here, expert parallelism, tokens are dispatched using here fine-graded FP8 quantization, reducing here the communication volume. This is beautiful. And then they said, you know what? And I mean, here you see that they really thought about how to optimize this further, because they do not have 100,000 GPUs. They have to be smart, they have to be clever, and they have to be real expert in their field. And they said, yeah, you know what? We just came up with a new data type, a logarithmic floating point format with log FMT n bit, where n is the number of bits with the leading one bit as the sign bit. And by mapping the activation from the original linear space to the log space, the distribution of the activation is now more uniform, and it's better and improves the performance. And I have to tell you, amazing. Read more about this in the paper. And then they focus, of course, about hardware-aware parallelism. And they tell us here, we further optimized here DeepSeek version 3, given our old version 2. And they said, you know what? We avoid a tensor parallelism because we have two better things to do. We enhance the pipeline parallelism and an accelerated expert parallelism. Now, what I find absolutely interesting is here this accelerated expert parallelism. And they say, yeah, okay, we have here a communication at speed exceeding here particular thresholds, but they say our new all-to-all expert parallelism implementation, DeepEP, is open source and is enabling high-efficient expert parallelism. So if you are into this, here is the GitHub. Really interesting. I just started to read this. I want to understand it. I do, unfortunately, don't have the time right now, but hey, have a look. It's great. It is, as you see, an MIT license. And yeah, interesting release. We have already 7,600 stars. An efficient expert parallel communication library, open source by DeepSeek. Next point is, I mean, there you see how much thought they invested here. Did it not just a brutal force of 100,000 GPUs, but what they did not have in hardware, they optimized here simply in smarter networks. Intelligent networks for AI. In their study published today, May 14, 2025, here DeepSeek AI, and hey, congratulations to all the authors, a beautiful paper. I love this paper. they also have kind of an outlook here on further technological developments that they are currently trying to implement. And they say, yeah, we are interested here in co-packaged optics, so incorporating silicon photonics to enable higher scalable bandwidth or enhance energy efficiency. Lossless networks, nice. Adaptive routing, and they explain here what I want to do. Efficient, fault-tolerant new protocols, and dynamic resource management. Really interesting here. Responsiveness for latency-sensitive application. They are not just implementing here with brute force and 100,000 GPUs. It is simply amazing to read their ideas, to see their experiment, their validation data, and then how they decide to continue. So, absolutely love this paper. And you know, at the end of my video, I always give here the authors here their own words. This is their conclusion. By addressing the limitation of current hardware architecture and proposing here actionable recommendation, the paper provides here a roadmap for the next generation of AI-optimized hardware. So you see, it's amazing. If you are limited by hardware, but you are not limited by highly intelligent experts in their field, and you bring those teams together and you form them in a startup, it is simply amazing what you can do. You can outperform the biggest global corporation from Microsoft, OpenAI, XAI, whatever you call them, because even their current model are state-of-the-art or leading state-of-the-art. And therefore, I'm absolutely fascinated by this topic. And when the new model R2 will be released, I think we have now a good base understanding of how they built their base model for R2, and then we can have a look at the specification for R2 in a later video. If you enjoyed this, hey, why not subscribe, and I see you in one of my next videos. Oh yeah, just forgot, if you're interested here also in the integration here, and I have this video already on Theorem Prover and the next generation AI, how they want to improve here the mathematical reasoning, the causal reasoning with Theorem Prover regarding here especially DeepSeek. I already have a video out that explains here this particular part of the next AI generation.